Okay, so I will present my paper entitled Towards a Smart Multimodal Image Registration Process. So this presentation will be divided as following. First, I will start by introducing the context and the objective of our work and the problem statement. Then I will detail the architecture that we propose and specifically the monitoring phase of this architecture. So my work is within a MAPE-K project. In this project, we aim to deliver data on the body reaction and material behavior during magnesium degradation. So the project is expected to generate a vast amount of 2D and 3D data from different modalities, and we aim to join this data with a multimodal image registration process for better analysis. In my work, I'm interested in registration of two inputs from different modalities taken at the same time point, either 3D to 3D data or 2D section to 3D volume. Now, in the following slide, I will give an idea about our data characteristics and the aspects of heterogeneity of this data. So I go to explain the first heterogeneity aspect through this example. So in this example shows niche and stained histology section and the output after segmentation. The segmentation is needed to make the historicity registration when we use a rigid registration. So, but on the other hand, we notice that the histology data are heterogeneous in terms of staining. As shown here, there are several staining methods. In addition to the previous heterogeneity aspect, our data is collected from different modalities, so several modality combinations are possible. And the third aspect is the data structure. So after, for example, in this figure, we have different examples of data from different provider institutes, and the data is structured in a different way from one database to another. After explaining the data characteristics, I go to explain the registration process. So the system first takes the input and segment them. In this step, the user provides manually some relevant information, such as the lower and upper threshold. In the second step, the system registers the two pre-processed inputs to compute the transformation matrix. In this step, also the user have to provide relevant information as the parameters of the registration. The third step is the transformation. So in this step as well, the user have to decide the workflow of the registration. In this example, our workflow is segmentation, then registration, then transformation. So from the last example, we concluded that numerous and complex steps have to be done by the user manually. So to fulfill the previously mentioned limits, we need to reduce the user interventions with a fully automatic process and perform the registration in a dynamic way to support more than one modality combination. So, because according to the literature, we noticed that the most of the work are supporting a specific modality combination, the registration of only one combination. So according to our literature review conclusions, we observed that the work in the field of the image registration are more interested in the executive layer using different registration algorithms. Namely, they are interested in how to perform the registration of sets of data with the same characteristics belonging to to the same modality combination. So the question here is, do we need the system to execute the process, or rather decide the process? Actually, if we aim to reduce the user intervention, the executive layer is not sufficient. We need a smarter system that decides and interacts with its context and accomplish its task with the minimal human involvement. That's why we decided to inspire from the architecture of the autonomous systems to propose a smart registration solution. So in the following slides, I will explain our proposed architecture. We inspire from the architecture of the autonomous systems based on the MAPE-K loop. The MAPE-K loop is composed of a data layer and 4 steps: the monitoring, analysis, planning, and execution. And in the following slides, I will explain the different modules of the proposed architecture and how we applied this architecture on the registration process. So for the data layer, in our case study, is composed of a reference database containing the information about the structure of the data and how this data is stored in each external database. And also it's composed of a rules database and the behavior history database connected to each other to store the behavior of the system and the information about the executed registration process. So now I will detail the different modules of this MAPE-K loop. First, in the monitoring phase, by definition, the system detects the changing of the system context. In our case, the image data in input are representing the changing context of the system. So the system is required to adapt its behavior running an appropriate image registration workflow according to the characteristics and modalities of the image in input. So after that, the relevant information extracted in the monitoring phase goes to the analysis phase based on this information and a set of predefined rules. The system recognizes the characteristics of the modality combination given as input, and this analysis is forwarded to the next step, which is the planning phase. In this phase, the system suggests a set of predefined registration workflows as a plan of decision. So in this scenario, the following is the suggested workflow to execute. So in the execution step, the selection of the workflow to be executed can be either done by the expert of the domain, who is the user, or randomly in the beginning by the system, and then the system stores the information about the registration workflow execution and the accuracy of the output, the accuracy of the registration in output, and put this into the behavior history database. And after many iterations, it builds an historical of the system behavior. Based on this historical, the system improves the choice of the workflow selection. Now back to the monitoring phase. We are interested especially in this step as it is more critical to collect the relevant information to get later the analysis. So in our MAPE-K loop, we represent the monitoring phase by the extraction module, and this module is responsible on extracting the relevant information and subdivided into 3 sub-modules. So first, the relevant information of a scan can be found in the meta file of the scan. So our extract metadata submodule aims to define the meta file location and the text pattern used in the meta file. Also, the relevant information can be included in the header of the image file. In this case, an external decompression plugin is required to read the information in the header. And third, the relevant information can be concluded from the image itself. For example, the information about the staining method in the case of an histology image. So for this aim, to recognize the staining of an histology section, we implemented an algorithm composed of 2 main steps. The first step consists in identifying the colors based on a K-means algorithm. The second step of the algorithm is based on a composed thresholding. So we tested our recognition algorithm on a dataset composed of 400 images collected from different databases from the University of Oslo, the University of Sfax in Tunisia, and containing supporting 4 staining methods: H&E, Telludin, Blue, Masson, Stricom, and Vancosa. And we got the following results. So we get a neglected number of false positive and false negative output. To conclude, multimodal registration is complex because of the specific characteristics of each modality. The data is heterogeneous. For this, we proposed a novel architecture for smart registration flows to avoid the complex user intervention. We implemented an enhanced histology to city registration process through the recognition of the staining method and the improvement of the histology segmentation. And the results of the segmentation based on the staining recognition should be assessed by the experts of the domain for sure. Thank you.